Let's take a look at 9.16. On a humid day in the summer, the mole fraction of water can reach as high as 0.0287. This deals with Dalton's law of partial pressure. Matter of fact, it's a pretty straightforward one. And remember, there are two different versions of Dalton's law of partial pressure. One of them deals with mole fractions. It says that the mole fraction of gas A, well, it says the partial pressure of gas A is equal to the mole fraction of gas A times the total pressure. Well, in case you've forgotten, the mole fraction of A is simply the moles of A divided by the moles total. In this problem, they've given you the total pressure. That value is going to be different for every person there. And they've given you a mole fraction for water. And they just want to know the vapor pressure of water, or the partial pressure of water, rather. So it just becomes a matter of multiplication. The pressure of water is equal to the mole fraction of water times the total pressure. So we punch that into our calculators and we wind up with 0.0302498, and we've got 4 sig figs there. It looks like 3 sig figs there. So our answer should have 3 sig figs. 1, 2, 3. 0.0302 ATM. That's it for that one. Now let's take a look at the next one. All right, let's take a look at 9.82. Magnesium metal reacts with hydrochloric acid, yada, yada, yada. The gas that forms is found to have a volume of 3.557 liters at 25 degrees Celsius and a pressure of 747 millimeters of mercury. Assuming the gas is saturated with water vapor at a partial pressure of 23.8 millimeters of mercury, what is the partial pressure of the hydrogen gas? All right, let's say that we panic and we say that we don't have any way of doing this. We can't figure out how in the world to solve this. Well, let's just plunge in and begin doing what we can do. Let's see what we can do with the information that they gave us. And the great thing about gas laws is gas laws always give you big pointers if you simply label what you got. So let's see what they gave us here. They told us we have a volume of hydrogen gas, because that's the gas formed in the reaction, of 3.557 liters at a temperature. Oh, come on. Do they think we're idiots that we won't notice that they slipped us the Celsius? So we're going to convert that to Kelvin, even if we don't wind up using it, simply because the very existence of the Celsius scale offends us as human beings. Then we've got a pressure of 747 millimeters of mercury. And this is where they're very ambiguous. But they mean for this pressure right here to be the pressure total. So let's go ahead and label it pressure total. Ah, my pen's not cooperating with me. Go away. Stop. There we go. So they mean for that to be my pressure total. So we have a temperature, we have a volume, we have a temperature, and we have a pressure. And it looks like we may be headed to Pivnert. Let's see if we can see what they're telling us again. Assuming that the gas is saturated with water vapor at a partial pressure, and assuming the gas is saturated with water vapor at the partial pressure of 23.8 millimeters of mercury, what is the partial pressure in millimeters of mercury of the hydrogen gas? Okay, I see what they're doing now. This is a classic laboratory experiment. In the classic laboratory experiment, which we sometimes do, sometimes don't do in lab, you take a flask, you fill that flask completely filled with water, and then you actually turn it upside down while it's completely filled with water in a big old bucket of water. You then take another flask where you're carrying out your reaction of hydrochloric acid and magnesium to generate the hydrogen gas. And this flask is closed and stoppered, but your stopper has a little hose attached to it. And that hose runs from the top of the flask underneath the water and into the upside down flask. As hydrogen gas is generated, it begins pushing water out of the flask, right? The hydrogen gas is lighter than the water, so the hydrogen gas goes into this flask and pushes the water out. So the water leaves the flask, and based on the volume change inside that flask, you can measure your volume of hydrogen gas. The only problem is, in addition to the hydrogen gas you generated, what other gas has to be in there? Well, you're going to have some water vapor in there, or gaseous water, naturally, because it's collected over a big bunch of water. So that's what they're having you do. They're having you do the math behind this very classic experiment. Well, part of this classic experiment is that you measure the total pressure of the room. So they did this in this little bit of write-up that they gave us, and they told us that we've got a total pressure of 747 millimeters of mercury. They then tell us that the water vapor pressure is 23.8 millimeters of mercury. Now, why in the world how in the world will we get that water vapor pressure? Well, you can find tables of water vapor pressure. And when you do it in lab, you actually go to this CRC, which is a big, thick book of constants, and you look up the water vapor at the temperature that you're operating. Well, according to Dalton's law of partial pressure, the total pressure is equal to the pressure of water plus the pressure of hydrogen, right? Because the partial pressures of the gases sums to the total. So we can calculate the partial pressure of the hydrogen gas by taking our total pressure and subtracting the pressure of the water. Now, why in the world would we want to do this? I mean, true, it's awesome to do something that we can do, but what in the world do we want to do with that pressure of hydrogen gas? Well, if we have the partial pressure of hydrogen gas, we know the volume associated with it. We know the temperature at which we're working. We can use Pivnert to calculate the number of moles of hydrogen gas. And that's what you're doing in this experiment, kind of. They're asking you it in a backdoor fashion. So let's get that partial pressure of hydrogen gas. 747 minus 23.8 millimeters of mercury. Go to our calculator, and we get 747 minus 23.8, and we get 723.2 millimeters of mercury. All right, so that's part one. They're wanting grams of magnesium. We don't know anything about the magnesium used in this experiment other than we can quantify the hydrogen product. So let me step out what we're going to do here to get part B's answer. Step one, we're going to take that pressure of hydrogen gas and get it to moles of hydrogen gas using Pivnert. Then we're going to take that moles of hydrogen gas and we're going to use that reaction they gave us in the little box there to go to grams of magnesium, just like we would in chapter 6. So let's begin using Pivnert. They gave us we solved for a pressure of hydrogen gas of 723.2 millimeters of mercury. Well, in order to use Pivnert, we have to have ATM. So we need to do a quick conversion. And that gives me 951.6 ATM. So now I substitute into Pivnert. Going back to using Pivnert here. So I've got the pressure of the hydrogen gas, 0.9516 ATM, right? So I've taken that partial pressure of hydrogen gas and I'm plugging it into Pivnert. They told us the volume way back up here, right? This was given to us in the problem, 3,557 liters. We now need to solve for a number of moles. 0.0821 is our constant. Liters, ATM, moles, Kelvin. And our temperature, 298. Solve for N by dividing both sides by 0.0821 and 928. Switch colors just to avoid things getting a little bit messy. 0.9516 ATM times 3.557 L. I'm sorry, my son looked at my lectures to help with a class that he's taking, and he said my lectures looked like a rainbow had a car wreck. Because I'm always switching colors. But at any rate, we punch that into our calculators and we get our number of moles. That's a 0 right there, right? Punch that into my calculator. And that gives me 0.1383 moles of hydrogen gas. So that ends step 1. Now we want to take that moles of hydrogen gas and go to grams of magnesium using our chemical reaction. So I have 0.138 moles of hydrogen gas times, well, I've got moles of hydrogen gas. I want to get rid of moles of hydrogen gas because I'm interested in moles of magnesium. Well, the only way I can switch substances is if I have a chemical reaction. According to my chemical reaction over here, which has gotten very, very small. Let me zoom in for it real closely again, right? 1 magnesium for every 1 hydrogen. 1 magnesium for every 1 hydrogen, so it's a 1-to-1 ratio. One-to-one ratio. I don't want moles of magnesium. I want grams of magnesium. And I go to my periodic chart, and it tells me that for every 1 mole of magnesium, I have 24.305 grams of magnesium. I'm having deja vu. I really think I have worked this one before. Times 24.305 equals 3.363 grams of magnesium. And there's your final answer to B.